Hello, everybody, and welcome. We heard that the software question is solved, so I might skip the presentation. As somebody with a roboticist background, I built like 2 shitty printers already, and hopefully not so many shitty softwares, but I still think that none of them are actually solved. So I will present you one interesting case study from our company. One of our biggest undertaking since, I think, migrating to a different kernel, which was replacing basically the engine mid-flight. Sorry, and that's not István hanging on the jet engine there. So it was a big takeaway how we changed the whole software from being a direct modeling tool to a parametric tool. I will shortly introduce the problem space, so what does that actually mean? Then we will take some time travel. Then we will talk about engineering challenges. And of course, finally, we will try to draw some lessons. Ways to design. So I was hardly thinking about how to get an analogy from everybody's life, like to understand what direct modeling and parametric modeling is. First, I came up with, the concept of a sculptor and one of an architect. But then I was thinking that maybe most of you already used a software in your life which resembles this kind of complexity. So thinking about sculpting, I came up with Paint. So Paint is a software where you can quickly ideate quickly draw your ideation on the canvas. You see immediate effects of it. You can quickly modify, you can quickly prototype your ideas. The only thing is that if you make a change, that's permanent. So you have to restart the whole process again. Basically, it gives you big fluidity, but it doesn't give you a possibility to build complex things. On the other hand, Photoshop is more like blueprinting. So it's for putting together complex projects. You have a sophisticated layering system and effects where if you change one layer, that propagates to all the layers, and you have a composite effect of your design intent. You are able to prototype more complex ideas. You can play around with them. You can go back and you can actually modify a layer without destroying your previous work. So if we go to our domain, CAD, direct modeling is like Paint. So you have the freedom to modify your model by pushing, pulling, dragging the different parts. So you can pretty easily concept not so complex designs. It gives you a great flexibility and it's really easy to learn. You don't have a high complexity curve, a learning curve. But what happens if your client or even you want to change your past design? You are stuck because you have to restart from the beginning. If you want to use this flow, you have to plan everything ahead and be conscious about all your decisions. So that's the point when parametric modeling comes in place. Here, just as with Photoshop, you have the possibility to travel back in the time and change a parameter of a model, which will then propagate to the present, and you will immediately see how your design intent is manifested. By this, you can actually build up really complex models, and you can play around. You can have many design iterations, and when when a client or somebody is asking for a change, you can easily create those changes. You can save up a lot of cost. Also, this flow can integrate it easily to simulation or any generative design or analysis tools. So great, we wanted to have this in our software. We wanted to build this, but how, right? So we need to go back in the past. So we needed somehow to time travel. But how to build a time machine, right? So we had an old engine and we wanted something like this, right? So we wanted to travel to the future, easy peasy, right? We just take the wires and everything will work. Not really. So we had the questions like, is our current architecture flexible enough, modular enough to play around and extend it somehow to be able to support this kind of flexibility? This was one question. The other thing was our constraints, like we needed to keep our existing user-facing APIs and flows up and running. So this was really hard. And I want to talk about these challenges. We had many, many challenges. I selected just a couple of them, which I considered important. But I think those are really interesting. So the whole, like how we started the development is already a good thing to talk about it. So the problem statement was, how do you plan and execute a major restructure while minimizing the engineering costs, right, and risks? It's not an easy thing. Why? Because, usually what happens is that people start building a shadow system and then they are replacing or merging it with an existing one. And that is really, really super risky. Also, like probably with your own experience that long-running monolithic developments or refactors usually are or too expensive or hard to predict, like to estimate, and usually they result in an underperforming design. And you are not able to validate, all the design decisions early on in the track to minimize the risks. Just to show the sheer, amplitude of our project. So this is like, the project lasted finally 2 years. Originally, the engineering estimate was 1.5 years. We did not miss that with too much, but just, like the kernel code, which the sheer size of the code grew to 552,000 lines of code. And this is our commit history throughout those 2 years. It was a really intensive period. We started as a team of 4, in the first 4 or 5 months when we were doing the first iterations, and then gradually we grew up to a 20 engineers team, which was basically 3 teams. And later on, of course, before the release, this was extended to the whole company, like the user, like the UI team and the rendering team and everybody joined to our effort. Most of the code was written in C++, and we did not have 2 or 3 years like big companies, big major companies. And yes, it was as you can see, software, like software development is an art. It resulted in a fantastic collaboration. So how we try to minimize risk? So what we did basically is that we created early prototypes in the beginning of our journey. So thankfully our system was already somewhat modular, so we could play around with it. This is our early first prototype from our staff engineer who actually made this working, and we had a nice scripting interface which validated the idea itself. And then for a long time we were like in this kind of analysis paralysis, like should we start? It's probably a big investment, or shouldn't we? And I must say that here the engineering took up the lead, and we actually went in a guerrilla mode, and we decided to make a second prototype where we had real questions to answer, which were really important, and critical part of the journey, like how our naming system should work, validate if it will really work, how we can extend our current wrap around the solid body kernel, is it modular enough, how much code we need to reshuffle in our existing tooling, and such. So we started, and then the question arose that, okay, we are developing now the new engine, but we need somehow to keep alive the existing modeling flow. How can we do that? Of course, the first solution is to keep 2 code paths. This is probably, and as it proved out, it's not sustainable on the long run. So actually, what we did is that, as I said, our whole architecture is really modular, and we build the new components around the existing kernel functionalities. We introduced the interpreter for the history evaluation, the history tree, the naming mechanism. We pushed down many of the modeling functionalities from the tooling to closer to the kernel. So we were able then to get building blocks which we could reshuffle and move around and replace. And our existing flow then was kind of rerouted to the same functionality, like our existing direct modeling users were going through the same path, but at the end, their modeling effect was just, like appended to the history tree and squashed. So they basically did not see the change. But underneath, we were able to validate the naming system, for example, during that period. Also, we need to introduce a special schema for versioning the different data representations. Like old users were using one data schema, and the new users needed another one. And actually, there were also a beta group which needed a third one. So that was something which we needed also to do. Before the product launch, end of the beta, basically we discontinued the single engine. So what was our single engine became the engine, and we needed to clean up everything. So this had immediate implications on the software. First of all, we needed to migrate 15,000 tests, basically, which were from the old branch. We needed to migrate it to history-compatible tests. When we exposed the app actually to all the users, definitely the memory usage was increased because we used more sophisticated and more complex data structures in the memory. Also, workspace load performance, like how quick the users were able to get their design loaded, was kind of degraded for some existing users. And runtime performance were affected. So, yeah, and everything needed to be as fast as before, right? In order to tackle these problems, we needed to come up with real clever engineering solutions. So one of the solutions to actually decrease the memory footprint of these operation, like tracking this operation, was introducing the introduction of special data structures, which were the patch containers. We actually had a C++ Dev Meetup on these, so you can check them out in the link. We used heavily memorization for all the modeling operations because, like calling the kernel and re-executing and putting the kernel to recalculate all the modeling operation each time is very, very expensive. So we tried to cache those, and we needed to come up with a really clever system to know if those memoization hits are still valid or not. We also needed to introduce a complex dependency tracking system with different dependency graphs. We actually call these topology line graphs because those topology attributes are actually tracked throughout the model, throughout the history, how the model is changing. So these are just a couple of solutions which we needed to come up. And yes, and then we released, right? And our crash rates peaked. Because out of memory issues, when the user started to open like workspaces which were actually on the limit before we deployed the new engine. So we need to do something with those. And also, just in time, we got another request from our backend guys that, hey, the sync costs went up crazy because the workspace size is huge, like we made measurements, and so we needed to address those ones too. So then we found out that, okay, so a lot of serialization data we stored in JSON format because it was convenient, but now we need to go to binary serialization, and we need to drop those in a blob in the database. And we actually could save up a lot of space, and so Sync guys were really happy. Then also, as I mentioned, we had load time performances. Like in some cases, it was degraded. One nice example is this one, when we looked in a workspace where one of our users actually modeled, a layout of a building brick by brick, right? So. This is not a usual use case, but still it shows that the system is not yet robust enough, so we needed to tackle these ones also. The other thing which we faced, and we knew about it, but we weren't aware about the effects on our existing customers was user data integrity. What does that mean? That is like all the value of the user is there, or IP of the user is the design which they actually put together. So don't touch that, and try to preserve that forever, right? In this new system, like in design history, we needed to introduce naming because we needed somehow to propagate, changes from the past to the present throughout the model changes, and we needed somehow to know from which topology the change came. And I was thinking about to come up with a good metaphor for this one, or analogy, and I came up with this example. Like John goes to the bank, and he wants to open a deposit account, and then they ask who are you? And he's like I'm John. Okay, we have like billions of Johns. We need something more specific, and he says I'm John Taylor. Okay, whatever, but more specific. I'm John Taylor from New Hampshire. Fine, 200,000 John Taylors. So we need somehow to have a unique identifier for you, because otherwise we are not able to open your account, and we will not be able to match you when you will come back and you want to grab your money. In CAD, we have something similar. Like we have here a filling, and we extract it to a cube, and we fill at one of the edges. So how do we know how that topology which is there, how that from where it came originally? We need somehow to have a good system in place which can track and uniquely identify all the topologies. If we miss any of these and we are not able to match them later on, that's data loss, because the design will blow up. We won't be able to recreate the design for the user. And that that means we have actually a really complicated dependency tree where the topologies are actually inheriting, names from each other. Sometimes this can be really interesting. Like here, if we split the topology, we had here an edge. How we know, how we uniquely identify that? What usually we do is we use the surrounding faces, we use the surrounding edge names, vertex names, and if nothing helps, then we have, at least we have a local coordinated system, and we use the geometric naming, meaning the relative positions of those from the local coordinate systems. The other problem of the naming is that you can imagine we can have millions of topologies in these models, and we are generating millions of IDs in the memory. One of the things is that this occupies a lot of memory. The other thing is that you have to be really, really super fast to access these. After we released, we got interesting results in matching, for example. Here, the matching took 2 minutes and 25 seconds. That's crazy, right? So something is high wired there. So we needed to tweak all our naming algorithms to be super fast. On the other hand, we needed somehow to clean up all the references after they went obsolete. So sometimes the topologies are dying. And we made, a project to have a kind of garbage collector for naming, and we just tried to draw the dependency trees of these names, and we came up with something like this. It's crazy. All these entities who are or referencing or owning or, semantically owning, or in the C++ sense, or just they are holding some reference to that name. And we needed to somehow to put together a system which cleans up after itself, because the memory usage and the load time performance issues which came from loading back all the dead names were critical. Yeah. The other thing which affected, user data integrity was versioning. So what we mean by versioning? So how do you ensure backward compatibility of your models with history, right? So we had originally a workflow where we extracted the filling, we created a cube, we filleted it, and then we kind of split it, that part. So, and one of the programmers are changing the modeling function for the extrusion, and we got something else at this step, and we are trying to reapply the whole operation, features in the timeline upon that. So what will happen? We don't know, right? So anything could happen. So actually what happens is the model will immediately change. We will not get the same design. An altered model is data loss for the user. So we can't let that happen. Versioning is really hard because it's really impossible to. It's impossible. You don't have too many solutions. You do code versioning, like you branch in the code. Now imagine that after a while that is kind of not sustainable on the long run because your code will be bloated. The other thing is code duplication. So you include each and every version in your binary, which will then, some of the companies actually do this with the whole UI actually wrapped, and it will result in a bloated binary. That's also not scalable. So the other thing which you can do is modularization, where you try to break out functionalities which do not change that often, and you are able to version that, and you are faced with the dependency, how you need to manage each and every time. And it's really hard because versioning, it's almost impossible to introduce later on because you have already old working non-deterministic behaviors, and you can't actually rely on anything to validate that your software is deterministic. Even the mathematical functions you are using can change, and then you are faced once again with non-determinism. Or the kernel itself is non-deterministic, though they argue that they are, but you have to validate that. Or you have like platform differences, right? So the same hash implementation on one platform, it's a slightly bit different on the other one. And once again, you have non-determinism. So it's really, really a hard problem. Or you can be on the verge of a tolerance, you know, like, because all the modeling operation are done with a tolerance. So floating point precision, whatever. It's super hard, and it's super hard to check, even not to maintain, but even to check. So after we released, we were kind of trying to track if these models were altered. So we introduced a testing system which was kind of checking if the re-evaluation of the whole modeling tree is resulting in the same geometry or not. How we did this? Actually, we did by calculating the topological hash of the model. The topological hash is basically put together by hashing all the different topological sub-elements and having one unique hash for that geometry. And we also tried to do a geometric mismatch if there we had a clash. Okay, so we did not answer, versioning, but we still wanted to answer this question. So how we are able to ensure our customers will be able to reopen their designs even after 20 years and get the model which they left there before. We know that the system is not deterministic, and we are not able to guarantee that. So we came up with an answer which was persisted execution, meaning that we actually persisted and reloaded the whole model. So every modeling operation was persisted to the disk, and we were able to reload it upon load. You can imagine that like a smart snapshotting of the workspace. So this guarantees model reloading integrity on the reload, but doesn't give you any guarantee on re-evaluation. So it's like a Castle card, like you will get back your Castle card, but upon you touch it, we don't have any guarantee that it will stay intact, because it's a really hard problem. And also by persisting the whole thing, we had a tremendous improvement on load performance, because we were just putting back everything in the memory, so reading back everything in the memory, and we didn't need it to re-evaluate anything. Of course, we needed to track if this is healthy, so we needed to monitor the reload success. And we came up with a dashboard which we are using now each and every day. So the aim of having a low persisted execution is natural, because that guarantees you that you are able to get back the customer's model. If that fails, you will go in re-execution or re-evaluation, where you don't have any guarantee, as we saw before. So our aim here is to push down the persisted execution reload error to 0. Actually, it's under 0.7%, which is really good, but we are putting a lot of effort in actually bisecting each and every issue we get back in order to find the root cause for it. So what lessons we drew from the whole journey? One of the lessons was that I will talk first about the failures. So one of the failures we did that we missed the severity of many things which went our radar. So we were not fully prepared for workspace mismatches. We did not do any load performance testing early enough. We did not knew that back at that time that we will have really hard issues because of this. So when we were in beta, we got back the first, serious feedbacks upon this. So, and we did not really well estimate the impact of the memory increase back at that time. So we knew that we will consume more memory, but we were not aware of the fact that many of the workspaces were already on the edge of, our memory limit. So we needed somehow to support those. And of course, we were really reactive when it came to data integrity issues, because as you see, it's not an easy thing. So many of these we discovered on the fly, getting feedback from our customers. So what were our lessons? So one of the lessons is that when you start these big projects, is that you have to not to stay in paralysis, but start and do prototypes early on to validate the biggest technical questions. In our case, it helped a lot to gather enough confidence, at least for engineering, to start the project. And of course, as I said, a lot of help was provided by the fact that we already in the beginning, we were striving for good modularization and thinking in a platform and not, like horizontal solutions. One of the other lesson is like it's super hard to write, deterministic software if it's possible at all. It's really hard. And if you can't do that, you have to somehow work around. And because users' data is really important, you have to keep the user data integrity intact. And some people might not agree who are product focused, but I think for engineering it's really important always to think ahead the product, to open up possibilities, even platform-wise, for future product requirements. And of course, test and benchmark for performance from day one, really. Even if your system is not grown up, you have to test that. And I will close with a good visualization, which I stole from our CEO. So how the whole replacement of direct modeling to parametric went on. It was a group effort. Thank you.